Hello students, welcome to the fifth lecture on mechanics of machining. In the last lecture, I introduced with tool nomenclature. In this lecture, I am going to tell about the conversion of tool angles. So let us just see that what are the various type of tool angles in different systems. American system. In American system, I said that if we make three orthographic projections, in those projections we can show the angles. In each one I can show two angles. So if we see the front view of the tool, then we are seeing that back rake angle. It is also called top rake angle. Then we are having end relief angle, and we are having in the top view we are having side cutting edge angle, and we are having end cutting edge angle, and this one is the nose radius that is apparent in the top view. That means nose radius is there. And I also told that your radial direction in SA system is this. That means depth of cut is you are taking in this direction. Okay. And feed is naturally in this direction. That means in this direction there is a feed. Here in the top view the tool is moving like this. In the side view I can see the side rake angle, and also I can see the side relief angle. So side rake angle and side relief angle, these are the tool angles of a single point cutting tool in ASA system. Then in ORS system also we can see the angles. In the top view we can see principal cutting edge angle, which is complementary of side cutting edge angle, and we can get auxiliary cutting edge angle. And in the cutting plane it will be apparent that inclination angle. Inclination angle can be seen in the cutting plane, and we can see the orthogonal rake angle in the orthogonal plane. That means we can see the slope of that surface in the orthogonal plane. That's what it is, orthogonal rake angle. And then here we can also see the principal flank angle in the orthogonal plane. Then similarly we can make one auxiliary orthogonal plane. Main cutting edge is there. Based on the main cutting edge you have made one orthogonal plane. Similarly based on auxiliary cutting edge also you have made one view, that is auxiliary orthogonal plane, and in that you are seeing that there is a auxiliary flank angle that will be visible here. That is also the part of ORS nomenclature, orthogonal rake system. It is also called continental system. Then we have British system, that is called maximum rake angle. Here in the top view we designate one plane, means if we want to cut a section here, in that plane the slope of that rake surface will be maximum. So it will be called a plane of maximum rake angle, and this is inclined with this radial direction. This inclination angle is called theta m or oblique plane angle. You are seeing it here, and in the top view of course you will get principal cutting edge angle in the same way. You will be getting auxiliary cutting edge angle here, and you will get orthogonal plane here in the same way in MRS system, in which as usual you will be getting principal flank angle, but you will not designate here the orthogonal rake angle here, because that is not this system. Okay, orthogonal rake angle also you can tell. There is of course relation between systems, but you have to specify only 6 angles. So 6 angles are sufficient. ASA system also I am specifying 6 angle and one nose radius. These 7 elements they provide tool signature. So similarly here also I have to give 6. So why I will be telling this angle orthogonal rake angle when I am telling the maximum rake angle in this plane? That means I am cutting a maximum rake angle plane here this section, and this is maximum rake angle, here the slope is maximum, so it will give idea that how the chips are flowing here. And then similarly we will make auxiliary orthogonal plane in which I can show auxiliary flank angle, and this is complete. Okay, so this is this system is there. Now we come to this one, NRS system, that is normal rake system, normal rake standard, and in this it is international system. In this international system, in the top view you are showing in the same way, there is a principal cutting edge and there is auxiliary cutting edge angle is there. In that there is no difference with the other two systems, except that there is some difference in SA system. In SA system we tell side rake angle, so side rake angle is 90 degree minus principal cutting edge angle, and but there we also tell end cutting edge angle. End cutting angle edge angle is same as the auxiliary cutting edge angle. So this is basically same in all these systems, auxiliary cutting edge angle. And now here we can take a cutting plane here. Now we take the cutting plane, and in that cutting plane I can see the inclination angle. See, it is inclined because it is oblique cutting, so inclination angle is non-zero. Suppose inclination angle is 0, that means it is orthogonal system. And then I can take a orthographic view here, you get a normal rake angle, so you get here on this plane you are seeing that normal rake angle, it is in the normal plane. So this you have seen in this one. So difference is that in the ASA system, rake surface is specified by two type of angles. One is along the feed direction how it is sloping, other is that radial direction how it is sloping. So you have got top rake and back rake. But in the orthogonal rake system, you are showing its slope in the orthogonal plane. In normal rake angle, you are showing its slope in the normal plane. That normal plane is basically perpendicular to the cutting edge. And then you have auxiliary cutting plane in the same way. Then we have got auxiliary normal plane. Okay, so here auxiliary normal plane, you are having auxiliary flank angle. So this is the flank angle here. That's what you are able to see here in the auxiliary normal plane. So this is NRS system, that is international system. Now we have got four type of systems. We want to see the conversion. That means if I know the 7 elements in one system, 7 elements means including nose radius. So nose radius is basically same in all these systems, but other angles are different. Now you want to convert from one system to the other system. Then how you will go about that? Question is that why we want to study the conversion from one system to the other system? It is, reason is that different researchers may tell their results in different systems. So therefore we must understand, if we want to map from one system to the other system in order to understand the other works. One can decide, you can decide, I will follow only SA system because it is very simple. Of course SA system in some sense it is simple also, it is convenient sometimes for tool grinding etc. But sometimes normal rake system gives better idea about the mechanics of the cutting. In fact, sometimes if you want to do some analysis in a proximate way based on the orthogonal mechanics, if you want to get inference about oblique cutting, then instead of side cutting edge angle, you generally use normal rake angle. So normal rake angle can be in that case called true angle. So that one thing is that sometimes if you want to do analysis, then normal rake angle system is better. In the normal rake angle system, whatever is your rake angle, normal rake you have got, that can be called as a proximate rake angle, and that you can use in even orthogonal formula. If you have got, you can use that. So one thing is that we need to know about the conversion, etc. Second thing is that this exercise will actually help you to visualize all the angles, and it is a good exercise. You get such type of situations where there are three-dimensional surfaces in other fields of mechanical engineering also. So this is a good intellectual exercise. It is better to understand these concepts. In many books this is omitted, and in many places this is not taught in detail because it is little bit painful sometimes to understand. From you have to know 3D coordinate geometry or vector method, but even then it is worth studying. So we are going to study this one by one, that how we convert from one system to the other system. This I am going to discuss now. We will move somewhat slow in each slide, and we will show you that concept. So let us see that suppose we just concentrate on converting the angles from ASA system to orthogonal system or vice versa. In that case, how we can go about that? I will have to make one reference plane which can be considered common in both the systems. In the reference plane, when I take the view of that tool, I will be getting principal cutting edge angle. This is principal cutting edge angle. Then if I cut a section in this one, that means something like radial plane, if I am cutting, then I am getting section Y in Y direction, then I am getting back rake angle. Back rake angle, in a crude way you can see that back rake means you towards your side. That means you have put the tool like this, and in this tool you are having this plane is like this. So this is the slope. Whatever slope you are seeing in this slide, that means it is towards you. That point is up, and towards you it is sloping. So it is something like that this point was up and it is sloping. This book is horizontal, but I have made it sloping. So something like this. So this way it is coming that back rake angle, and then in the cutting plane, you know the cutting plane is plane that contains the velocity vector, and also it contains the cutting edge. So that cutting plane, it is orthogonal to the reference plane. In this angle, in this plane, you are getting inclination angle. This is the inclination angle that is visible to you. Inclination angle 0 means it is orthogonal cutting. Then here you are having orthogonal plane which is perpendicular to the reference plane and cutting plane, and in the orthogonal rake angle you are observing in orthogonal plane. This is orthogonal rake angle, this is back rake angle. All these relations are there. So now here I have put the labels in detail, and we are taking the section. Suppose there is some tool, I am showing the top view. If I take a section YY, here I am getting end relief, and I am seeing the back rake angle in SA system. In SA system, if I take a section XX here, then I am seeing the side rake angle here, and I am seeing the side relief angle here in SA system. So SA system is complete with these three views. One view is this, other view is this, third view is this. This time we have taken sections, and cutting plane is in this direction. In the cutting direction, this BC point goes here. So you are having cutting plane, and here this is inclination angle. And if I take the orthogonal plane, I just rotate it here. That means in the cutting plane and orthogonal plane, basically the heights will appear you to be same, because both are the vertical type of plane, although one plane is 90 degree with the other. So in this orthogonal plane, you will be getting principal flank angle, and you will also get orthogonal rake angle here. That type of thing you will be observing, and observe that motion, that here point A, in this view that point A has gone here. that it will be shown here. Similarly, B is here, that B point is here. Like that you have to designate that what are the things which are going. Suppose this point T is there. Now T, if I take the section of the T, in the top view there is one T, but here if you see there is one T in the surface and one in the T dash, and we can say T double dash, and one is at the same level. That means height. If two things are at some particular height, one point is this, another point is this, in the top view both the points will appear as one entity, but actually in the other view they will be distinctly apparent. So you have to visualize these type of things. Concept of your drawing are here useful. So this we have to see, and now we will see that how it can be converted. So we are going to maybe next slide here, but before that let us discuss about orthogonal and normal plane. What do you mean by orthogonal plane? Of course, orthogonal plane you know very nicely that this plane is perpendicular to the cutting plane and also the reference plane in whatever system we use. And in that, if we draw that this type of projection, then we see the principal frank angle in a very apparent way, and orthogonal rake angle appears here. That means the slope of the surface will be distinct here. This point will be up, other point is down. So by this we can know that this point is actually up. It is not the same elevation, not same height level from the surface. So elevation is different, height level is different. So this difference is there, this difference is there. That is why the chip will slide in that fashion. Okay, that means chip will slide from here to here like that. So this is sloping like this. Now normal rake angle is actually, it is not orthogonal to the that cutting plane, rather it is normal to the cutting edge. So that means it is inclined in a way that suppose you have got one book and this is the orthogonal plane, that title of the book is visible, but that has been, suppose I tilt it a bit so that it becomes perpendicular to this thing. So you can say that this surface actually becomes tilted compared to that previous surface. So that type of phenomena will happen. This is really not 2D diagram. Here I am showing that Z0 is the normal. Then in that particular direction, means out of the plane, you have tilted it and that axis has become Zn, and in that system you will be measuring that normal rake angle, and both the axis, vertical axis will be inclined by an angle that is called inclination angle. That means inclination angle. Suppose this is the vertical, is the cutting velocity, but since my plane has tilted, so therefore in the plane whatever that line is, that it is no longer vertical, it is inclined with the vertical, and that inclination with the velocity is actually called inclination angle. That means how much is the extra incline. If the inclination angle is 0, then the orthogonal plane and normal plane both coincide. So this you have understood. Then we will go to in detail. We want to study that how these things are related, and we are going to study this one, that here, yeah. Now let us go to tool angle relationship in ORS and ASA system. So we want to go from ORS to ASA, we want to understand. Here I have designated these angles in terms of the symbols. Alpha B back rake angle, alpha S is side rake angle, alpha O is orthogonal rake angle, I is the inclination angle, delta P, delta S, gamma E is the you can say end cutting edge angle, and gamma P is the main principal cutting edge angle, or it is basically 90 minus side cutting edge angle. And then you have got some point T, which I am showing here that it is, this is T and another point is Ty, and we are taking different sections. So what is shown that this point T, how it will be shown in the other view. In the other view it is here, but that one and this one is showing that Tx dash. So that means there are these levels are different. That means at the surface you are having T and here at the top you are having Tx. So because it is sloping. So this difference between two T's, that means one without dash, other it with dash, that will be apparent in the section across YY plane, but it will not be apparent in the top view. Similarly, you see that when I take a section across the cutting plane, now my BC is looking simply straight line and B point is there. But when I take the section in the cutting plane, then I am seeing that this BC prime, that is up, and BC, this one is down. That means I am clearly seeing the slope here. That means because the height, top view doesn't show me the height. Height above some level like sea level or something, it is not showing, it is at the same level. Reference plane is showing same, but here the height will be apparent. You have to identify that in the cutting plane this is basically height. So vertically that point is down. That is why you are saying that the cutting edge is inclined. Similarly here also it is down. So you can always imagine in terms of that thing that you have something horizontal surface reference plane. From that, whether it is coming down towards the earth or it is going away from the earth, that type of idea you can have about the slope, then it will be easy for you to visualize, and you have to do it at many goes, then only you can understand this one. Now here, now if we go to this one, so points A, T and Q on the base plane, that means are transformed on the pi y plane, that means section across YY plane as AY, TY and QY respectively, and they are further transformed on pi x and pi 0 plane also. Concept is that you have to keep seeing the height. Suppose the height in orthogonal plane and YY plane will appear to be same. Some point is at some height in XX plane, its a height in YY plane will also be same, because you can understand that I am taking this section in the XX and other is YY. Only in the top view height will change. So cutting edge on pi C plane inclined at an angle I is transformed on orthogonal plane. Points BC and BC prime on pi C plane, that means cutting plane, becomes B0 and B0 prime on the orthogonal plane, and point Bx on the pi x plane corresponds to B0 on pi 0 plane. Point Tx on rake face in pi x plane is transformed to corresponding point Ty on the rake face in pi y plane. So like that we have got these type of relations, and now let us see that how the equations will go. So let us concentrate on the inclination angle. Inclination angle is getting measured in the cutting plane. So in the cutting plane, how should I measure the inclination angle? Tan I is equal to BC into BC prime divided by AC BC prime. That means horizontal distance in this one, and in the vertical direction how much it is going. So vertical distance, suppose it is going this much, and divided by horizontal distance, so BC prime, that this one. How it is related to the other slopes etc., this can be done like this. AC BC prime actually in denominator, concentrate on that. AC BC prime, that is the horizontal distance, that is basically same as AB in the top view, because AB has been projected. So AB on the top view is basically same. This is AB, and BC prime, because it is showing the height difference. So here it is something like this, that if you have one point here Tx, okay, Tx on this point here Tx dash. So Tx and Tx double dash. This is top view, this one is Tx double dash on the top surface. This is the basically corresponding to topmost point, and Tx, and this is basically the surface, because this point is at the surface. So Tx dash minus Tx dash, that means minus Tx dash this. So then we get this difference. This difference is what? That means this difference, let me make it like this red. This red point is basically showing me what? That it is showing that vertically how much this horizontal surface of this place is down with respect to this B. Okay, because this may be corresponding to the top BC prime and this is corresponding to the bottommost that point. So that means this is what it is showing. So that is how that it is Tx double dash minus Tx dash. Tx double dash, Tx is the lowest point here and Bx is at the same level as Tx dash. So that is why Bx is at the same level as Tx dash. So that is why you are getting this type of thing. So you are getting Tx dash minus Tx dash divided by AB. Now this Tx double dash, that means from here to here, Tx double dash is what? Topmost plane type of thing. That means I have got a tool and in that I put some plane level thing at the top. So it is basically the highest point. It is at the same level at which BC prime is there. So it will naturally look, and Tx is what? Tx is at the bottom surface. So it will naturally look same in the YY plane. In YY plane Tx double dash becomes actually equal to Ty double prime. So it becomes Ty double prime, that height becomes. And here minus Tx dash, that will remain as it is, and we put AB. So having written this type of relation, whenever you have difficulty in the visualization, you try to put coordinates of each and every point, then you can very easily understand. Slope means, suppose there is a surface, it is horizontal, no slope. But if the surface point comes down in the vertical direction, then there is a slope. If surface point can come in this one, but there are two ways. This point can come down like this, or it can come down in the other direction. It can come down towards my side. It can, two ways that it can lower. That means this is like this, and I am lowering, I am tilting it like this. Or I can tilt it like this, is it not? That means my hand is there, I can raise my hand like this, or I can raise my hand like this. So this is, both the things are this one. So I am showing with the book, this is horizontal, now this is the slope, I have tilted it like this, or I can tilt it like this. It can, suppose this is a horizontal, I want to make vertical, it can become vertical like this, right? And it can also become vertical like this. So there are two directions you can do the rotation. This point you have to understand. So there is, if you write this thing, whenever that there is a one point or the surface is lower, means towards earth, compared to the previous point, naturally that time you have got slope. So here Tx double dash is basically Ty double prime, because it is in the same orthographic view, and means height wise it remains same, and Tx dash is this. Now Ty double dash is basically AC, Ay, this point is Ay, Ty double prime is on the top, into tan alpha b. It is obvious tan alpha b is equal to basically height divided by the base, and Tx prime, this will be apparent in this view in which side rake angle is visible, that will be minus Tx prime Bx into tan alpha s and divided by AB. This much will be there. So Ay Ty double prime is basically same as AT, and Tx prime Bx, this is same as Bt in the top view. So this is AT by AB, you are getting AT by AB, and you are getting tan alpha b, AT by AB, and you are getting tan alpha b. That means you are getting the back rake angle, okay, tan alpha b, AT by AB. Now AT by AB is very much apparent here, AT by AB. So this is 90 minus this one gamma p, this is basically gamma p, because this is the interior angle. So this is gamma p and this is gamma p. So I can write it AT by AB means sine gamma p. So we have written sine gamma p. So sine gamma p into tan alpha b is coming here, and then I have got minus cos gamma p, because bt by AB is basically cos gamma p, and this is tan alpha s. So we have got sine gamma p into tan alpha b back rake angle minus cos gamma p into tan alpha s is equal to tan I. So that means inclination angle can be obtained if I know sine gamma p, that means principal cutting edge angle, and I know back rake angle, I know side rake angle, then I can calculate inclination angle. If it is orthogonal cutting, then I will be 0. Then I can find out approximate relation also whether the process can be considered orthogonal or not, depending on this type of situation. Sin gamma p tan alpha b minus cos gamma p into tan alpha s. So one relation we have obtained like this. Now let us try to understand the other relation. Similarly, we can find out understand orthogonal rake alpha 0 can be evaluated. How alpha 0 can be evaluated? We have to go to orthogonal plane. In orthogonal plane, we have got, this is the orthogonal plane, that is which is shown in this OO. In between there is a point Q here at the center. So when I am cutting here, then this point can go to this one. Orthogonal rake can be evaluated from tan alpha 0 is equal to Q0 prime and B0 Q0 prime. Okay. So here suppose Q0 is point just on the surface where I have cut. Okay. So let me just go to this one. Yeah, it is basically here. That means this Q point is here. That Q point will come here. Here I had not shown earlier. Now I am showing Q is somewhere here, and this will be tan alpha 0 is equal to B0 and Q0 dash. That means tan alpha 0 is 0, B0, and I am cutting it on the surface. So this is B0 and multiplied by we have got here on the top, we have got Q0 and Q0 prime. So that means this is the orthogonal rake angle. Then the points QY double prime and QY in the pi y plane, they correspond to the points Q0 prime and Q0 in the orthogonal plane. So if we see that QY in this one is corresponding to Q0 point there, and this will be explained here. So here that will be B0, so this will be shown here, and then it will be Q, therefore QY double prime QY, that will be equal to Q0 prime. That means this height is same, and now this tan alpha 0 can be basically written as QY prime plus QY into QY prime. So QY prime is this, and this is equal to this. So that means this is basically the vertical height. So in a way that basically I can say and divided by B0 and Q0 prime, because here I am cutting and I am calling it basically Q0 prime. So it will be basically this one. So you got B0 Q0 prime here, and this is this one. Now here tan alpha 0 will be actually equal to Tx prime in this view, Tx into Tx prime. If we say that this is Tx prime, and this will be Qy prime, and B0 Q0 prime, that basically can be written as B0 Q0. So that means this is basically B0 and Q0. So B0 Q0 is basically same as point B and Q here, B0 Q0 here, because this is B0 Q0 prime here, that Q prime point is here. So this becomes parallel to BQ. So this is basically BQ. Once we have established this, then it becomes very easy. Tx prime is equal to Bx Tx prime into tan alpha S. So this is, in this view, it is apparent, Bx Tx, this one. And similarly Qy prime is actually, it is apparent that this will be Qy prime y into Ty into tan alpha B and divided by BQ. Now Bx Tx prime is basically same as Bt, and Q prime y and Ty here, that is in this view YY plane, that is same as Qt. So therefore you will get Bt by BQ tan alpha S and plus Qt by BQ is equal to tan alpha B. Now Bt by BQ, this one, it is nothing but sin gamma P, because Bt by BQ, this is orthogonal to that. So this angle is gamma P from horizontal, so this becomes 90 minus gamma, so Bt by, this becomes gamma P, so Bt by BQ is equal to sin gamma P tan alpha S. Similarly Qt by BQ, Qt is in this one, Qt by BQ in this. So this will be here shown in the top view, this is cos gamma P into tan alpha B. Now you have got a relation between orthogonal angles also. Tan alpha 0 is equal to sin gamma P tan alpha S plus cos gamma P into tan alpha B. Suppose gamma P is equal to 90, that means side cutting edge angle is 0, that means cutting edge is perpendicular to the feed direction in the top view. In that case, you see tan alpha 0 will be tan alpha S, that means side rake angle is same as the orthogonal angle in this one. So it is side rake angle that which will decide mostly the flow, not that one. That has some effect, but here that factor is cos gamma P only. Here gamma P becomes 90, so cos gamma P here 90 0, sin gamma 90 is equal to 1. So that means in a very rough way we can say that orthogonal angle will be more close to the side cutting edge angle in a AC system. That is what we have obtained this relation, and otherwise you have got this type of relation. I have tried to explain with the help of this one, but you have to see it again and again and visualize yourself. Then only you can know, yes, these are the relations. Now, basic concept you have understood. Otherwise, by rote, if you understand, then there will be lot of difficulty. And I am trying to explain, make you visualize with the help of these pictures. So it is better that you yourself will do that. And I have given enough hint here. Now about so inclination angle and that relation you have obtained, and principal cutting edge angle gamma P is very easy, it is simply equal to 90 minus gamma S. So having known this thing, we have understood that how the angles from AC system are converted to orthogonal system, or we can also have vice versa. So these things you have already understood, and this one. Now we are telling something from ORS to NRS. ORS to NRS, mainly there is a difference of the rake angle. So how the rake angle will be differing? In a way, apparently it appears that tan alpha n, that means that particular slope in the orthogonal system may be more, but there it will get slightly reduced depending on alpha n, that means depending on inclination angle. That point we have to show that how it is rotating. So here again you have to visualize this relationship is almost same that which you get something when you derive the relation for universal joint, where two shafts are, you know, that connected, but they are skewed a bit and they are at angle I. Similar type of thing we are getting. Here normal plane is taken as the reference plane where the rake angle alpha n is measured. Now this plane is inclined to the orthogonal plane by an angle I. That means I is the inclination. In a way, I have a orthogonal plane like this book, and now I have inclined towards you, or I have inclined towards me. So that means the plane has become inclined. So this plane is inclined to orthogonal plane by an angle I. Therefore, the point Q0 in the pi 0 plane is rotated by an angle I, and its projection Qn is obtained as shown in the figure. That means projection is taken like that, and the rake angle can be evaluated from this one. Tan alpha n will be basically Q0 prime Qn. That means basically the height portion here, that this surface in the orthogonal system, what was the tan alpha 0? It was Q0 prime, that means vertical elevation difference, and B0 Q0 prime means horizontal difference between 2 points. That ratio of these two, that means first divided by the second one. So you have that type of relation is already there, tan alpha 0. Similarly, now if I am doing that, if I have inclined, so that height difference, that in the top tan alpha n is equal to something numerator divided by denominator. Denominator remaining same, but in the numerator height will slightly reduce, because in a straight way there was this height between these 2 points, and when I have tilted, then naturally the height has reduced actually. Vertical height has reduced, this has come down and this has come down. So vertically height has reduced because you tilted it. Suppose you make 90 degree, naturally it will become 0. So that means there will not be any difference there. So this is what the rake angle alpha n can be evaluated Q0 prime Qn and Q0 prime B0. Q0 prime B0 is same, but Q0 prime Qn is basically Q0 prime in the orthogonal view multiplied by cos I. Means height will reduce by a factor of cos I. That you can always visualize that. Suppose this is a vertical line, if I rotate it by I alpha, then you can very well make out that by making a planar diagram here, that how this length is changing, because the previous one will become then hypotenuse, and this will become the base, and this is alpha. So then naturally this will be Q0 prime cos I, and therefore you are getting tan alpha n is equal to cos I into tan alpha 0. That means orthogonal rake angle is reduced by this relation. Normal rake angle becomes cos I times that tan alpha 0. So that type of relation you are getting. If I is equal to suppose 90 degree, I is equal to 90 degree, that means tan alpha n becomes 0. I 90 degree will never be there. Generally inclination angle is 5 degree, 6 degree, no? It is of that range, but I can be 0. That means it is a orthogonal cutting, no inclination angle is there. In that case tan alpha n will be same as tan alpha 0. So this relation also has come. So like that you can actually derive ASA to ORS, MRS to NRS. In many books these relations have been given for your understanding and for broadening your knowledge about the 3D things. I have introduced these things and you should practice this one, but each derivation may take time actually. If you do that, maybe 1 hour for you to understand, but this way it has been derived and these relations are available in the books. So these relations, so when day to day life you can just take these relations and we can plug in and you can get the angle. Suppose geometric equations required for converting two angles from other systems can be obtained in a similar way, and these are like in American system. I can obtain tan I is equal to tan alpha b inclination angle by this formula, and normal rake angle is obtained by this. Well, this is things are given in American system. You can obtain the inclination angle and you can obtain the normal angle, which is also called true angle sometimes. And gamma p is equal to 90 minus gamma s. Cot square delta p is equal to cot t square delta e plus cot square delta s minus tan square I, and this is cot delta p n is equal to cos I cot delta P like this. These are the relations, and in continental system tan alpha n is equal to cos I tan alpha 0, and similarly cot delta Pn is equal to cos I into cot delta P. Delta Pn, delta P is the clearance relief angle here, and this is the corresponding relief in the normal system. In British system, you have tan I is equal to tan alpha m into this relation, and you have got also tan alpha n is equal to this much relation. Now here it is not the only way to understand the transformation. You can use 3D coordinate geometry. There are many methods. In fact, if you see the old book of that Amitabh Bhattacharya about metal cutting mechanics, he has given several methods to do that, 4-5 methods. So one method is, suppose vector method for angle relationship. You can make the vectors, you can make the lines, and you can say these are the vectors, and the condition that these vectors will be planar is that the triple product is 0. So using this type of relation, you make one vector, another vector, then put the condition of making triple product of 0, then automatically you will get relation. This can be done in mathematical way, but I have told you in such a way so that it helps you in the visualization. It is more physical. You can, I think, appreciate. I am following what I am taking the projections. I am seeing the height of the points in one plane, and I am seeing that what happens in the other plane. By that way, I have done derivation. There is a relation between alpha m and side rake angle and back rake angle is this: tan alpha m is equal to under root tan square alpha s plus tan square alpha b. That means in maximum rake angle, this is the relation. So simply, suppose there is only slope in one direction, side rake angle, but alpha b 0, then that is the maximum slope. That direction you have to do. Suppose you have got one straight road which is sloping. Na? This is the sloping. In that case, you very well know that only if you go in the direction of that road, then you encounter maximum slope. Na? Suppose you start moving perpendicular to that direction, you will get 0 slope. I have inclined this like this. I am going from here to here, I am getting maximum slope. If I go from here to here, 0 slope. In between, if I follow this path, then my slope will be reduced, because between two extremes it will change. So that is why that it happens tan alpha m is equal to under root tan square alpha s plus tan square alpha b. I can derive it also very nicely for this. I am, say, suppose I want to derive in your presence. That is why I have not already made this slide. Suppose this is y. Suppose I make a 3-dimensional picture type of thing. This is x, y, and this is the vertical plane here, vertical line z. So x, y, z, I can say this is x, y. It is basically out of your screen, but I am showing at a 45-degree inclined line x, that you very well understand. And suppose I have this point here, then I have got this point here, and I have something like this point here. So supposing this, you see that this point is O, is the origin. Let us say this point at the top is A, so that basically height OA is fixed in all the cases. Let us say it H. So what will happen, that in this x plane, in this rather xz plane, you have got this type of concept, that suppose this projection was A, this that means this length was A and this length was B. That means this length was, so I can say ABC. So let us say OB was equal to A and this was equal to B. Okay. So in that case, what would have happened? That means I would have got something like tan, and I will get tan alpha S, suppose is equal to H by A type of thing if I define, and tan alpha B I define. I am just trying to derive it. Tan alpha B I define H by B. That means this divided by B. So that means if you move on the plane, in the plane there are 3 lines. AB line is there, AC line is there, and BC is there. and now if you move from A to B, your slope will be this. If you move from here to here, the slope will be this. Now if you move at any other plane, suppose instead of that I move at point P, that means OP, that means AP line. So in AP line, you will encounter how much slope? Downward you are coming the same distance h, but horizontal distance is changing. So that means your angle will be different. So since the height is same in all the cases, so therefore in this particular case, if the horizontal distance, this distance is minimum, that will give you maximum slope. So that means what is the condition that this distance should be minimum? That means maximum P will give the maximum slope. If I go from A to P, you will encounter maximum slope provided I drop from OA perpendicular on BC. So basically OP is that 90 degrees. So that is what. Now the question is that how much is that OP? So if I can do like this, suppose this BC line is there, equation of line BC is x by A plus y by B is equal to 1. And if I drop, O is a point of 0, 0 point. So if I drop the perpendicular, you know the equation, how do I find the perpendicular distance? Let us call it D. So D will be simply 1 divided by under root 1 square plus 1 by B square, right? So therefore tan gamma M in essence will be basically H divided by D, that means H divided by 1 by A square plus 1 by B square, like that. Okay, now this one, 1 by S, 1 by A is basically 1 by A. So here you are getting tan alpha S is equal to H by A. So that means you are having, so if I also do tan alpha S square, suppose I take under root tan alpha S square plus tan square alpha B, then I will be writing under root H square by A square, right? And plus I will be getting, this is this will be H by D, sorry, that, okay, when you do H by D here, okay, tan gamma M is equal to not really H by this one, rather this will go up, so it becomes H by under root 1 square plus 1 by square. This is small mistake I have done, that you have just see carefully, that is why it is better that suppose I have done mistake but corrected. So it will appear that if you are attentive, you can make out that this is D is equal to this one, so it is H by this one. And here tan square alpha S plus tan square alpha B is equal to H square by beta square, which also comes out to be H1 by A square plus 1 by E square. So what does it show? That it shows that tan gamma M is equal to really under root tan square alpha S plus tan square alpha B. So this I have proved you for your purpose that you have seen. So this one, so like that you can prove that you should have some interest in doing this type of mathematics, then you can make it out. Now if I go to this one, till now we talked about single point tools. In the single point tools, in lathe machine, boring machine, we use that, but now we have to understand multi-point cutting tools also by the same logic, by the same type of geometry. Suppose example is that we can have milling cutter. In milling cutter there are number of teeth are there, and there is a chip space, there is a tooth space in here, and this is the periphery. In the same way we can define the radial rake angle, just like we define in the single point cutting tool. This surface is slightly slanted, so draw a radial line that becomes like a reference plane, and from here you are having this angle, and this is these are the cutting edge, this is a cutting edge, and this one, and usually these are at the helix also. So that means geometry may differ from in the axial direction also. This need not be straight. rather it is this tool is helical. So we designate the helix line also. We take a section here, we get some sort of rand here in the Frank surface, then we get it is slightly sloping, we make a principal Frank angle there with reference to that means whether it is radial line, here one, that means whether it is rubbing or not. Then this another slope may also be there, it is called first clearance angle, and then we can have further sloping, that may be second clearance angle. I mean to say actual tool geometry may be very complicated, but you have to define and we have to systematically understand, and this one is this one. So in the plane milling cutter, the helix angle is 0, that means cutting edges are straight and is equivalent to an orthogonal tool. The radial rake angle of these cutters are the same as the back rake angle of single point tool and is equal to the orthogonal rake because principal cutting edge angle is 0. Helical cutters remains in contact for a larger time than a plane milling cutter and they give smooth cutting. That is why we provide a helix, so that all of a sudden a particular tool doesn't lift hold the workpiece. Some point of the that particular edge is in contact. Contact is gradual, and so here that one different angles are used, and now you are having side milling cutter, different angles are shown 10 degree, 12 degree, 15 degree, depending on that. Radial rake angle can be more if it is a soft material like aluminum. Here I am getting 15 degree, some places I am getting 10 degree, and radial Frank degree angle is in 5 to 6 degree, that one. Similarly, you can have twist drill. There are two main cutting edges which are cutting. We are seeing that the cutting operation will go on the helix wise fashion. Here we define a helix angle. This point is called, this edge is called chisel edge, and here you are having, there is some, you see outer place cutting is there and other part of the body will be slightly inside so that it doesn't rub. So that is why we are calling it a body clearance. And in the same way, only thing that you have to visualize now, it is in the curved profile. Otherwise it is the same way. You have one cutting edge here and other cutting edge here, and in between that included angle is called point angle. Usually in most of the drills it is about 118 degree, particularly for steel, etc. And this one is this one. If you cut these sections here, then you can get the same type of thing. Here you can get rake angle, then you can get here the Frank angle, and then you can, and you have got the flute, that is space is called flute, in which the chips will flow in a helical pattern. Helix helps in bringing the chip out, and this is the chisel edge, and these points are this one. So it is that is this is lip length is called this, and cutting edge or tip. So here cutting occurs on the chisel edge and the cutting tips, and the chips generated travel up the axis of the drill through the flute. Through the flute they go. A section perpendicular to the cutting tip indicates the rake and cutting angle, and the rake angle, however, varies along the cutting edge and largest at the periphery. In this case, it is largest at the periphery. The average value of helix angle is around 30 degree for machining of ferrous, and 45 degree for, it can be for non-ferrous. For non-ferrous you have even more, and typical angles for HSS drills are point angle is 118, point angle is this angle, included angle. Cast iron also it is like this, aluminum 110, tool steel 130, and these are the chisel angles, and this is the helix angle. All this data is provided here. So this way that I have introduced you with different type of systems, that angle system. In this way we understood, we got some idea about the conversion of this one. Maybe when we discuss about the multi-point cutting operations, then we can again go back and can see that. So, but this understanding is very useful, although it may be little bit painful, because you have to visualize sometimes you can make the model by Fevicol or by any in wood. You can make the tool. Generally I make very big wooden type of, so that I can touch it and we can visualize about the angles. So here you can see only through pictures and you can get the idea, but actual 3D things you can make and you can visualize these angles. So this one, so for today only this much, and from in the next lecture we will study about the cutting forces, how do we obtain cutting forces in machining. Okay.